Okay, in the 7.3 quick check, we want to go through about 3 problems here. So first off, we have the electrolysis of a solution of lithium chloride. Okay, the solution, that's a very important part of this. So that means in here we have water, and we have lithium ions, and we have chloride ions. Okay, so any solution, we mean an aqueous solution, water in there. Okay, so the first question here says, draw the flow of electrons across this battery. Well, the fact that the battery says negative on one side and positive on the other, that means that this is like a little electron pump, and it's going to pump the electrons in this direction. So electrons are being pumped out of the pencil on the right through the graphite into the pencil on the left. So electrons are going from that way. Label the anode and the cathode. Well, there's a couple of ways to do this. One is you might memorize that the electrons always move from the anode to the cathode. Okay, and that just, that doesn't mean why it does. It just, is true. So we know the pencil on the right's the anode, the pencil on the left is the cathode. But the other part about understanding it, if the pencil on the left has electrons being pumped into it, then whatever chemical touches the graphite down here, okay, is going to gain some electrons. So we know that if you gain electrons, then that's reduction. And if that's reduction, then this side over here must be the cathode, because reduction always occurs in the cathode. In the same way, on the other side, okay, if the electrons have been pumped out of this pencil, that means if a chemical touches it down here, okay, then that's going to have it lose electrons, and losing electrons is oxidation, which means that this pencil on the right, that where it's touching, that would be the anode. And we can see that electrons do go from the anode to the cathode. And in fact, this is the anode and this is the cathode because of the direction the electrons are moving. Okay, what are the half reactions? Well, we stop and say, okay, here's the cathode. Here's a negative electrode, okay, because it's connected to the negative side of the battery. And here's a positive electrode because it's connected to the positive side of the battery. If it's negative, who's going to be attracted to that negative? And the answer is lithium. Lithium ions, positive lithium ions, will come over to the negative side. And because this is a solution, water will also will be over here in contact with the pencil. On the other side, we'd have the chloride ions would be attracted to the positive side, and water is one of the possibilities. So we have to say, okay, we want to do reduction. Now reduction, we look up here. If I want to do reduction, these are all written as reductions. There's lithium being reduced, and here's water being reduced. So these are the two equations that we're going to see. So lithium could pick up an electron and become lithium metal. Water, turns out, could pick up 2 electrons, become hydrogen gas, and 2 OH minuses. Now, which of these is actually going to occur? Now we look at our reduction potentials, and it turns out whichever one is less negative, whichever one is more positive, that's the one that's likely to occur, and so it's the water. So water is the one that's actually going to occur at that. So we have 2 possibilities, but only one's actually going to happen, whichever one with a larger reduction potential. Now for the other side, we have to say, well, we have chloride. Okay, so here's our chlorine, and we have water. So both of these reactions, they're doing oxidation, so we have to look for these chemicals, chloride and water, on the right side of the equation because we're going to run them backwards. And when they do run backwards, we're going to say they have an oxidation potential, in this case of negative 1.36 volts. And the other one would be an oxidation potential of negative 1.23 volts. So we're going to take these two numbers and we're just going to change the sign. So we're going to say, okay, what are our possibilities? 2 chlorides could turn into chlorine and give off 2 electrons. And water, 2 waters, could turn into oxygen and 4 H pluses and 4 electrons. And of those 2, which is more likely to happen? Whichever one has a larger oxidation potential. So we have negative numbers. So negative 1.23 is larger than negative 1.36. So again, it's the water that will actually do the changing. So that's how we use these reduction potentials up here, is to find out, once we have decided who's our oxidation, who's our reduction based on the charges on the pencils, then we go back and decide, okay, of those two, which is more likely to occur. So that's how we answer that first question. Okay, the next one's a little bit different, because now this is a molten salt, and molten, means melted. So we have this heated up so much, with a Bunsen burner, that it actually turns into liquid. So now we have no water involved, and that makes it a little bit easier. So on the positive side, okay, what's going to happen on the positive side? Well, who's going to come to the what do we have? We have lead, we have Pb2 pluses, and we have Br minuses. Okay, those are our two ions in here, and it's not a solution, it's just those ions floating around. And so who's going to come to the positive side? The Br minus. Okay, when it comes over there, what's it going to do? It's going to lose an electron. Okay, so we're going to have two Br minuses turn into Br2 and give off 2 electrons. So that process there is losing electrons. Losing electrons is oxidation. So this is the anode. Now at the other side, at the negative electrode, okay, the lead is going to be attracted to that. So what's going to happen at the negative electrode is it's going to cause the chemical to gain some electrons. So we're going to gain 2 electrons and become lead metal. And when we get that lead metal, okay, then that means this is reduction. So it's gaining electrons is reduction. And so this is the cathode. Okay, what's our overall reaction? Well, 2 electrons, 2 electrons. We put these together, they cancel out. So we're going to have Pb2 plus 2 Br minus turns into Br2, and that's a liquid, and Pb metal, that's a solid. Okay, what's the voltage needed for this? Well, we need to go back and get our numbers here. So we're looking for the reduction, so the reduction of lead. So E0 of our cell is equal to the reduction half reaction, and that's the one for lead, plus the oxidation half reaction, which is the number for our bromine. But again, we got to watch out, because bromine, since its oxidation is going to be turned around, we got to change the sign. So let's go back and look at our things, our equations. So here's lead and here's bromine. So lead, we're going to use that as is. That's negative 0.13 volts. That's our reduction. And we're going to add our oxidation potential. So here's bromine, and it's positive 1.07, but we're going to turn it around. Okay, so it's going to be negative 1.07 because we reversed the reaction. And now it's an oxidation potential, so negative 1.07. So negative 1.13 plus negative 1.07 equals negative 1.20. Okay, so that is the voltage of our cell. But the question says, what voltage would you need to cause this electrolysis to occur? So we're going to have to add at least 1.20 volts. Probably more, but at least 1.20 volts to cause this change to occur. Okay, the last question here is a calculation question, and it says a solution of copper chloride is electrolyzed for 20 minutes. That means we do electrolysis on it for 20 minutes with a current of 3.75 amps. What is the mass of copper metal that will be deposited? So implied in this question is the equation that copper 2 plus, because it's copper chloride, will pick up 2 electrons and become copper metal. So we need that little, for every 1 mole of copper metal, we're going to have 2 moles of electrons. We need that piece. Okay, the fact that we have a current of 3.75 amps, then that means that there's 3.75 coulombs going through our circuit every second. 3.75 coulombs per second. We're going to need that piece of information as well. So let's go ahead and do the problem. So we're going to start with the fact that we have 20 minutes, and we all know that in every minute there are 60 seconds. And now we can use our conversion over here that every second in this current, is going to be 3.75 coulombs of charge run through our cell. And because of Faraday, we know that there's 96,485 coulombs in a mole of electrons. That's the Faraday constant. And we know now from this equation that was not really said, outright. We had to kind of imply this, that it takes 2 moles of electrons for every 1 mole of copper metal. And then finally, we just look on our periodic table and we see that 1 mole of copper metal is 63.55 grams of copper metal. So when we do all of this, we get an answer of 1.48 grams of copper. And that's our final answer, 1.48 grams of copper. And that's the quick check.